Hi there, everybody. We are here to look at example 3 from our circular motion notes. So this one is a little different than the previous two examples we've looked at. Those two were horizontal circles, and this one of the first things I notice here is that this is actually in a vertical circle. Okay, so that's going to change things, where in the past we didn't really have to worry all that much about the effect of gravity. Here, gravity is going to matter. So we're going to look at two different locations, the top of the circle and at the bottom of the circle. So let's go down. Let's draw a free body diagram at both the top and the bottom to understand what we're dealing with. Okay, so let's take a look here. I've drawn the center mass of this object at both the top and the bottom. We of course know it's moving at 5 meters per second. And again, because it's going in a circle, it's going to be undergoing a type 3 acceleration, as we refer to it in our class, where that's a changing direction kind of acceleration. We also know this as the centripetal acceleration. That's always directed towards the middle, whether it's at the top, whether it's at the bottom. This is a directed towards the middle or a center-seeking acceleration. So let's focus on the bottom part here first, and let's draw our free body diagram there. So let's say we of course know that we're assuming here we're on Earth, and we are of course going to have the force of gravity, and that is a force that acts on the ball, and that's because of the Earth, of course. As always, it's directed downwards, and that's just how gravity is. Next, I have string. This thing is attached by a string. This string is going to exert a force. We call that tension. That's going to be an upwards force. Now, note that the acceleration is upwards. So knowing that there's an upwards acceleration, we know that the magnitude of this tension force is going to have to be greater than the gravity force. If these two were equal to one another, it wouldn't be accelerating. It would be moving at a constant speed, and it would actually be traveling off in a straight line path. Now we know, of course, that's not what happens. So we know that that tension upwards, okay, this is the tension upwards by the string. So that's on the ball because of the string. Has to be larger. It has to be larger than the force of gravity, since there's acceleration upwards. Okay, next up, we're going to talk a little bit about what happens here at the top. So let's zoom in with our object at the top. Now again, the assumption here is that it's traveling at the same speed. This is a relatively unrealistic expectation, which we'll talk a little bit about later. But once again, the acceleration is downwards. Of course, we're always going to have the same force of gravity. So I'm going to draw that. It looks like it's about 2 blocks, maybe a little bit more longer than 2 blocks. I'm going to draw it the same size up here. So it's about this big, roughly speaking. So it's the same as before. So that's the force of gravity. Again, still caused by the Earth. And again, the string this time is going to be pulling downwards. Now, I have no idea how far or how much. It may be bigger than the force of gravity. It may not be. So at this point, I'm just going to draw a downwards force. Again, understanding that it could potentially be bigger, smaller, or possibly non-existent. And that's something that will come out in the equations if we want. So for now, I'll just draw it kind of as a placeholder. It's going to be a downwards force. Now you might be saying, what about an upwards force? Okay, there are no other things in contact with this ball that's going around, so there can't be an outwards force. Again, that's a misconception about things going around in circles. There are no outwards forces on something like this. So let's go ahead, come up with a strategy, and we'll see what we can do to solve this. All right, so the things that we know here, we know, of course, the mass is 1 kilogram, the radius is 1 meter, it's traveling at 5 meters per second, and we're going to try to find the tension. This is our find quantity, and again, we're going to try to find this both at the top and at the bottom. So let's go ahead, let's continue with the strategy and see what we can do to find this. Since we've done a free body diagram, you can never go wrong by writing and starting out with Newton's second law. Newton's second law kind of is a catch-all. After we've dealt with a free body diagram, this is always a good place to start. Again, the thing we're trying to find in here is going to be part of the net force. So what we need to do is we need to substitute in the forces that we're dealing with. Let's deal with, I guess, the bottom first. I don't remember if that's part A or part B, but we're just going to say here we're dealing with the bottom. I'm going to call up positive for this part. If I call up positive, that's going to make the tension force positive, and it will actually make the gravity force negative. So I'm going to have a positive tension force and a negative gravity force. There's only two forces. That's what's going to cause the mass to accelerate. Again, because we're dealing with centripetal acceleration, I can make the same substitution I have in some previous problems. The centripetal acceleration is equal to v squared over r. And so I will make that substitution. So it's going to be m times v squared over r. I'm going to have the force of tension, and of course the force of gravity is times mass times gravity. When I solve for Ft, let me give myself a little more room here. When I solve for Ft, I'm going to end up with Ft equals m times v squared over r plus, since I'm bringing it to the other side, m times g. All right, and again, you can leave it this way if you like, or you might notice that there's a common m between these two, and we end up, if we factor that out, we end up with v squared, or sorry, m times the quantity v squared over r plus g. All right, and this gets it down into the things, again, that I know. I know the mass, I know the velocity, I know the radius, I know gravity, because we're here on Earth, and we're trying to solve for the tension force. So we're in good shape now to go ahead and implement, and I'll do that on the other side, behind the scenes, and we'll pick up together here in just a moment. Okay, so we've substituted numbers in. Of course, there's the 1 kilogram mass, the 5 meters per second. Don't forget to square it. We're dividing that by the radius of 1 meter, and of course, there's the acceleration due to gravity, which is the 9.8 meters per second squared. So that actually, if you do calculations, you end up with a tension of about 34.8 newtons. All right, so now let's take a look at our second part. The second part was to find the tension at the top. So what we're going to do here is we'll kind of rethink what's going on down here. And this is actually one really minor change, in fact. So what I'm going to do here is kind of rethink the fact that these two forces right up here were actually in opposite directions, which is why these here were plus and minus. But if you really think about it over here, both of these are actually in the same direction. In fact, the acceleration, the Fg, and the Ft are all in the same direction. So pretty much what this will make is our net force equation becomes Ft plus Fg equals mass times acceleration. We're going to go through pretty much the same exact substitutions, the same exact mathematics, and I will promise you, if you do the algebra, okay, if you do the algebra here, so some algebra happens. If you do this, you're basically going to end up with the force of tension is equal to mass v squared over r minus g. So again, very similar process. The one minor exception here, of course, is they are in the same direction. They kind of help each other when it comes to causing this mass to accelerate. So we're going to go over, we'll substitute these numbers in, and I'll catch you on the other side. Okay, so after doing the calculations, we end up with 15.2 newtons. And again, this is for the tension at the top. And we have 34.8 newtons. And this will be the tension for when the ball is at the bottom. Now, there was one last part to this problem. And that last part asks us to talk a little bit about what factor, I think it said, what factor made it nearly impossible to rotate this stone in a vertical circle at a constant speed. And I realized just now, actually, the word rotate is not the right word here. Actually, this is actually a revolution. Not that that really matters to the sake of that, but if I wanted to be correct, it should actually be a revolution. So let's actually talk about the terrible drawing that I can draw of a circle. But let's look at this point right here, and let's talk about the forces that act on it. And let's say it's going around the same direction, and so therefore it has this velocity here. Well, there would be a tension force. Let me get my blue marker. There's going to be a tension force pulling it inwards. All right? Gravity, as always, is going to be directed downwards. So this is the force of gravity in the downwards direction. So we have our velocity up. We have our tension directed inwards towards the center here. And we have the force of gravity, which is a downwards force there. So the combination of these two forces, okay, they actually add to give us a net force. So the net force here would actually be in a direction kind of this way. And notice that's not a net force that's in the direction towards the middle. So this is not just simply a centripetal force. Now, we're going to get rid of the net force, and let's talk specifically kind of two different kinds of accelerations here. What we have is a center-seeking acceleration. That's the centripetal acceleration. But this downwards force here, this force of gravity, is going to cause an acceleration down this way. And this downwards acceleration could be referred to as a tangential acceleration because it's, again, directed along a tangent line. If you think about this line right here, this would be a tangent. So this centripetal acceleration, okay, this one goes to changes the direction of travel. So that's one way an object can accelerate. The second acceleration here, this one right here, is going to go to decreasing the speed. Decreases the speed of the object. And again, that is a type of acceleration in physics. Now, again, if you think about this side, we have our free body diagram, we have the force of gravity down, and we have the tension force inwards. And what we're going to have here, once again, because of the tension, we'll have an inwards force. That's our radial acceleration. And here, we're going to have an acceleration downwards, once again, due to the force of gravity. And since the velocity is in the downwards direction, this is actually going to be an increase in speed. So again, that's our another way we can actually accelerate. So what factor makes it nearly impossible? And that would be, of course, this force of gravity, because the force of gravity is always directed downwards. Sometimes, as the ball tries to go up the one side, it's going to actually slow the ball down. As it comes down the other side, it's going to try to speed this up. So that makes it very nearly impossible to do this. Of course, you could maybe come up with some clever contraption that would somehow pull it up with the tension, but again, very unlikely. And so that's why we make this simplification to this question.